All right, so today we're going to talk about the ratio test. Okay, so this one is a pretty cool test. What we're going to do, we're going to let the series n equal 1 to infinity of a sub n be a series with non-zero terms. Okay, so number one, or A, if the limit as n goes to infinity of the absolute value of the ratio of the n plus first term over the nth term is equal to the number r, and that number is less than 1, then the series n equal 1 to infinity of a sub n converges, and it just doesn't converge, it converges absolutely. So this is the best way to prove absolute convergence in my opinion. Okay. Number 2, B, if the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to r, and that r, that limit, is greater than 1, then the series n equal 1 to infinity of a sub n diverges. Diverges. Okay? And the third, C, if the limit as n goes to infinity, absolute value of the ratio, the n plus 1 term over the nth term is equal to r, and that equals 1, so the last case, so that's all three cases. You can have r less than 1, r greater than 1, and r equal to 1. If r is equal to 1, then what do we say? The test fails. Okay, the test fails. So those are my three scenarios of what's going on with the ratio test right there. So if r is less than 1, converges absolutely. R greater than 1, diverges. R equal to 1, test fails. Okay, think about something where r is less than 1. Hopefully that makes you recall the geometric series. So let's, do a fake proof here. Geometric series. Let's do a geometric series where it's recursive. Okay, recursive form of the geometric series looks like this. To get the next term, we multiply the geometric ratio r times the current term. Okay, so to get the current term, we do a0 times r to the n minus 1. Okay, so what do we do here? Say we have series n equal 1 to infinity, a r to the n minus 1. Now, for absolute value of r less than 1, the series converges. To what? First term over 1 minus r. Okay, first term over 1 minus the geometric ratio. All right. Now, if the limit as n goes to infinity of an plus 1 over an equals r, then what does that tell me? What does that tell me? That means an plus 1 over an is roughly equal to r for big N, okay? So as n goes to infinity, this thing's roughly going here. Now, what does that mean? That implies that absolute value of an plus 1 is roughly r times the absolute value of an, which just so happens to be our recursive form that we found right there. Okay? So just, kind of an idea of where the ratio test comes from. It's built off the foundations of geometric series. All right. So let's use the ratio test to determine if a series converges or diverges. So, series n equal 1 to infinity, -1 to the n, times n squared over n factorial. Yikes! Okay? Anytime I see a factorial, I should automatically think ratio test right off the bat. Okay? And I'll show you why ratio test is a good guess in just a second. But first, I need to write my an term. So my an is -1 to the n, n squared over n factorial. If this is an, then an plus 1 is -1 to the n plus 1. Everywhere I see an n, I replace with n plus 1. N plus 1 squared over n plus 1 factorial. Okay? So how do I set up my ratio test? I take the limit as n goes to infinity, absolute value, an plus 1 over an. And so when I take this limit, I get the limit as n goes to infinity, absolute value. Well, what do I plug in here? I plug in this an plus 1, right, divided by an. Okay, now that's a lot of stuff in there. Okay, that's a lot of stuff going on there. What do I see cancel? I see some things cancel right off the bat. This cancels with this here. All I'm left with is -1 to the 1 power, which is -1. But the absolute value with the -1s cancel each other out. The rest of this stuff, since n is going to infinity, that's all going to be positive. So I can drop the absolute value bars and get the limit as n goes to infinity of, now drop my negative because the absolute value, I get n plus 1 squared divided by n plus 1 factorial, all divided by n squared divided by n factorial. Okay, now keep, change, flip applies here. When I'm dividing fractions, easy as pie. All you got to do is flip and multiply, right? So keep the numerator the same. N plus 1 squared over n plus 1 factorial. Change division to multiplication. And then flip, do the reciprocal of the denominator right here. Okay, now what I want you to note is this thing actually multiplies out to n plus 1 times n minus 1, all the way down to 3, 2, 1. This up here multiplies to n times n minus 1, 3, 2, 1. So I see some simplification going on here. The n's cancel, the n minus 1's cancel, the dots cancel, 3, 3, 2, 2, 1, 1, all cancels. So what am I left with? I'm left with the limit as n goes to infinity of n plus 1 squared over n plus 1 times n squared. Okay? So what's going to happen here? Well, my n plus 1 squared cancels with this 1 n plus 1. Okay, so that leaves me just n plus 1 in the numerator. So I get limit as n goes to infinity of n plus 1 over n squared. Now this is the form infinity over infinity. So if I L'Hopital, take the derivative of the numerator, I get 1. The derivative of denominator is 2n. And this actually limits to 0. Now 0 is less than 1. So what does this tell me? By the ratio test, the series n equal 1 to infinity of negative 1 to the n squared over n factorial converges absolutely. Pretty cool, pretty cool. So this one's going to converge absolutely. You saw the really nice trick that happened here, and the reason whenever I see a factorial, I automatically think ratio test, is when I see these factorials and I divide the n plus 1 divided by the nth term, what happens, the factorials end up killing each other off, okay? There ends up being a big old fight, and typically, you know, only one piece will survive, okay? And then, you know, we had some algebraic luck here with those simplifying, and our limit was not very hard to calculate at that point, and we got that it was less than 1, and so by our ratio test, since r was less than 1, it was actually equal to 0 for that one, then it converges absolutely, the series does. So pretty cool. And this technique is extremely important for us going forward. Okay, so gotta know it. Now, if I see factorials, I should think ratio test. I see powers to the n mixed with polynomials, exponentials, polynomials mixed together. I think ratio test. And so here's an example to illustrate that. Series n equal 1 to infinity, n to the 4th over 3 to the n. Okay, when I look at the an term, now, to me, an exponential in the denominator is definitely going to overpower the n to the 4th in the numerator. Polynomial time is not as fast as exponential time. So this term is definitely limiting to 0 as n goes to infinity. So the nth term divergence test doesn't really help us out here. So what I look at is the n plus first term. So take the limit as n goes to infinity of an plus 1 over an. So this is the limit as n goes to infinity. Well, these terms for n greater than or equal to 1, I mean, they are positive. An is positive. Okay, so we don't really have to even worry about the absolute values here because we don't have any sign switchers or anything. So I need to just write out the n plus 1 term. So I plug an n plus 1 in everywhere I see an n, 3 to the n plus 1, and then divide by n to the 4th over 3 to the n. So same thing here. And if you want to drop the absolute values, that's fine to do at this point. Keep, change, flip, n plus 1 to the 4th over 3 to the n plus 1 times what? 3 to the n over n to the 4th. Now, does anything simplify here? Well, this is where we've got to go back to exponent rules, okay? 3 to the n plus 1 is really equal to 3 to the n, same base, add the exponent. So the same base, add the exponents. So that's really what that is equal to there. And so what we see is, since this is equal to 3 to the n times 3 to the 1, these 3 to the n's cancel with each other. And what do I get? I get the limit as n goes to infinity of what? Well, I get n plus 1 to the 4th over 3 n to the 4th. Okay? And so when I take this, the form is infinity over infinity, right? So if I L'Hopital here, take the derivative of the numerator, take the derivative of the denominator, that's 4, n plus 1 to the 3 times the derivative inside is just 1. And then I get 12 n to the 3, okay? So the 12 and the 4 cancel, so I get 1 and 3 here. And then I still get infinity over infinity. So L'Hopital again, limit is n goes to infinity of, and then the derivative top is 3n plus 1 squared times derivative inside is just 1 again. And then I have 3 times 3 is 9, and then n squared. And so once again, these will cancel and I get 3. Guess what? I'm going to run through this game. What do I know is happening here? This degree is a degree 2, and then that bottom degree is a degree 2. Therefore, all we have to do is look at the coefficients. Like, you can keep running through this game if you want to, but your answer is going to be 1/3. Okay? What do you know about this 1/3 here? Well. 1/3 is less than 1. Okay? That's good for us because if it's less than 1, the ratio test the series n equal 1 to infinity of n to the 4th over 3 to the n converges. Absolutely. Okay? Converges. Absolutely. All right. Now, if it converges absolutely, then the series n equal 1 to infinity of n to the 4th over 3 to the n converges. All right? So absolute convergence implies that there's convergence, right? So just, if you prove something converges absolutely, then it definitely converges, right? If you were having trouble and it was like, man, I didn't really want to do all these L'Hopitals here, one thing that you could have done to skip through that, when you had this part right here, both of those factors there are written to the power of 4. So this is really like n plus 1 over n all to the 4th. And then what you could do is you could bring that limit inside here, and you see that this is an n over n. Both of those have a lead coefficient of 1. So really, as n goes to infinity, this goes to 1/3 times 1 to the 4, which gets you the 1/3 that you had here. Okay? All right, guys. So hopefully you can see how useful the ratio test is. We're going to do one more example with the ratio test. It's going to be very important for us going further.